First of all, I would like to thank the organizers for inviting me to this prestigious workshop and to show some of our research which we have done in the recent years. So I put some things together and called it Physics of Mantle Melting, Two-Phase Flow, Variable Matrix Viscosity and Density Effects. This is the outline of the talk. I would like to start with a light introduction and then go to the two-phase flow governing equations and concentrate on the rheology of the matrix, the melt porosity dependent shear and bulk viscosity rheology of the matrix in a two-phase flow system. And then we would like to see how these kind of variable viscosity influences some of our solutions, the porosity waves with variable viscosity. And then in the last part, I would like to move to the effect of density of the melt with respect to the matrix, because there are interesting effects if you are going to greater depth, where the melt might be denser than the solid. We will get some kind of standing porosity waves in this dense melt case. And I don't think I will find the time just to advertise that we are at the moment doing some benchmark initiative for two-phase flow in mantle convection. So let's start with this introduction. So where do we expect melting in a dynamic Earth? So this is my favorite slide to start geodynamics lectures and talks. We have hotspots, ridges, subduction zones, and so on. And where would we expect melting in the mantle? Well, this depends, of course, on the temperatures and the dynamics. So with the depth and temperature, we have the solidus and the geotherms. If we have upwelling material, then we would get decompressional melting, of course, in passive rifting and spreading ridges environments. Or if we have plumes or active rifting, we might have higher temperatures in the mantle to get melting at greater depth, a few hundred kilometers or even greater if the temperatures are even higher. Or even if the temperatures are not higher, but we have water, we may reduce the solidus temperatures in order to get melting for kind of subduction zones. So if we plug this back into our first slide, we have all these regions where we would expect partial melting and would be looking at the dynamic or the two-phase flow effects. Most oftenly, this is done in spreading ridges or in plume ridges, and this is exactly also where I would like to focus on the second part of the talk, or the last part of the talk. If we go to greater depth, transition zone depth, if we have very hot melts, very hot plumes there, whether we would, what happens with the melts if they might become denser than the solid in these environments. Okay, so this was the really short introduction, and I think most of you have seen this many times. Let's look at the governing equation which we usually solve. So this is the Mackenzie type formulation where we have the conservation of mass of the melt phase with the melt generation term here, the conservation of the matrix with a negative melt generation term. Phi is the porosity, the melt porosity, and F and S, the subscripts, stand for the fluid and solid respectively. We have the conservation equations of the momentum for the melt, which is the Darcy's law, driven by pressure gradients and buoyancy. And we have the momentum equation for the matrix with the pressure gradient and the viscous stress. And we have the conservation equation for energy, which is combined for the melt and the solid by just assuming an average velocity so we have only one equation for the energy. Of course, this implies that the properties, this is the assumption that the properties like density and heat capacity, that they are equal for the melt and the solid, which is kind of Boussinesque approximation, because here in these equations we assume different densities here, and we have buoyancy which drives the flow, but in this equation we assume same densities, which is of course something like Boussinesque approximation. So these equations are combined, coupled by the rheological equation of state and the permeability porosity relation, stress and strain rate, bulk viscosity, shear viscosity, and the permeability as a function of porosity to a power n. So within this talk, I would concentrate or focus on the viscosities, which are highlighted here, and on the densities, which are highlighted here, the density of the melt in the second part. Okay, so let's talk about the viscosity of the matrix. So if we have a partially molten rock containing a fluid phase, and we subject this to some stresses, pure shear, macroscopic pure shear stresses, we can try to find out the shear viscosity, and if we apply a homogeneous stress, we can derive the bulk viscosity or volumetric viscosity. In order to calculate or determine these viscosities or these rheologies, there are two effects which have to be accounted for. One is, which we usually do, is the mechanical weakening due to the presence of void, due to the presence of holes or inclusions, like a cheese. If you have holes in a medium and you subject this to some stresses, there will be stress concentrations in the regions between the holes, and there will be strain rate concentrations between. So you get a strain energy or strain rate energy enhancement, and you can calculate effective moduli or effective viscosity due to this effect. But at the same time, as the melt is sitting in the inclusions, you enhance or you increase the possibility or ability to for diffusion. So diffusion can take place much faster through the melt phase, so you get a second effect, enhanced diffusion, and you have to include these both in these effective laws. In order to formulate this, the most important thing is how is the melt geometrically distributed in the solid. So many years ago, these were the first attempts to describe this in a very, very early paper. So we talk about melt films sitting between the grains. We are talking about melt tubes sitting along the edges of the grains, and melt pocket sitting at the corners of the grains. And in recent years, these geometries, they have been experimentally visualized. I guess Uli has given in his talk examples of this, where we really see that the melt is sitting on interfaces as melt films or along melt channels, but also in melt tubes. So all three geometries, they are present in these laboratory examples. Or here the example by Su et al., in which we clearly see all these three geometries. But as the melt fraction increases or changes, the relative volumes of these three geometries, they change, and this is the important thing if you want to describe an effective rheology. So a student of mine, Jan-Philipp Kruse, and me, we are developing a simple approach which consists of 4 steps. First, we try to describe geometrically average an average grain, and in order to have the same size or the same shape of surfaces of this grain, we take this hypothetical pentagon dodecahedron, because this has the optimum or average number of surfaces, about 12 surfaces. We describe the melt geometries with this grain geometry, melt geometry in terms of pockets, tubes, and films, and describe this by an analytical or semi-analytical expression, and how to distribute the melt in these three geometries. We use a couple of parameters, 3 or 4 parameters. And then in order to constrain these parameters, we explore these parameters, the range of these parameters, by fitting it to laboratory data, to wetness data, how much of the internal surfaces are wetted by the melt and how many surfaces are dry. And then once we know these parameters, we can go back to our pockets, tubes, and films, plug this into a rheology law based on these pockets, tubes, and films, and determine an effective rheology. So I briefly go through these 4 steps. So this is a pentagon dodecahedron, hypothetically just as an average geometry of a grain, and not a real one, of course. If you cut out one of the volume associated with one pentagon, you get this pyramid, and then if you cut out one part of this 1/5 of this pyramid, you get this geometry, and you can describe all these elements of this geometry by analytical or algebraic geometric quantities. And this can be used then to determine the volume and the surface of these different geometries, like the pockets. You see at these edges, at these corners, we expect these pockets. So part of the melt pocket are sitting or assumed at the corners of these geometric bodies. The green ones are assumed the tubes along the edges, and then if we put a melt film on the face, we get this volume of finite thickness and prescribed geometries. So here you see the example of a tube along a grain edge. Here you see the example of a pocket sitting at the corner of 4 grains. So here the brownish part is the face where the tube is connected, and the red part is the interface between the melt inside the pocket and the solid outside. So these geometries can be analytically described. And then if we have a melt tube, we can put a melt film. So this is the melt film, which can be put along the adjacent faces, and we can describe all these geometries by a set of controlling parameters. One parameter describes the shape of these kind of pockets. So either we can assume very concave pockets or more convex pockets by changing one parameter of this geometry. We introduce another parameter which describes the relative volume of the melt sitting in the pockets with respect to the tubes, and another parameter describing the film thickness relative to the thickness width of the tubes. And we can put all these, and one parameter which is kind of dihedral angle characterized. And describing an analytical model, we can determine the volume and the surface of the melt phase and compare this so now we are in step 3. We can compare this to observations, laboratory observations. So there are data by Yoshino et al., Hirth and Kolstad, Garapek et al., where they determined the wetness, the amount of the wetted with respect to the total internal surfaces in a polycrystalline material as a function of melt fraction. So these are the data, these points are the data, and then playing around with our parameters, one can optimize or fit these geometries which we get to these observed data, and you see very nicely it is possible to fit these observational laboratory data. And for example, this fitting curve predicts that the volume fraction of the different films, pockets and tubes, that they vary as a function of melt fraction. So you start for small melt fractions with the blue one with the tubes, melt sitting in tubes, and then if you increase the melt fraction, the relative volume of the tubes decreases. The melt pockets, they remain more or less constant, but the amount of melt sitting in the films or in larger volumes wetting the grain faces increases with melt fraction. Now coming to the fourth step here, this is how to plug this information or this model into a rheological model. And here we use the approach which we have published a few years ago, in which we take this strain energy based effective viscosity, assuming spheroids, so you see for example spheres or ellipsoids with different aspect ratio. We assumed tubes according to this old NAFCO model, and then determine the effective viscosity as a function of melt fraction for these simple geometries. And you see if you have, for example, spherical inclusions, the effective shear viscosity drops to 0 after about 50% melting. But if you assume melt films or tubes, this is the black curve, that the viscosity drops much faster. And also the bulk viscosity.
Everything below that linear curve is associated with the shear viscosity model?
Yeah, this is the shear viscosity and this is the bulk viscosity. This set is the bulk viscosity and this set is the shear viscosity scaled by the matrix viscosity. Yes, and depending on these different inclusion shapes, we get a decrease of effective shear viscosities and more or less a 1/phi decrease of the bulk viscosity. And it should be noted that these models after Berkovici, Ricard et al. In the beginning of the 2000, that they use quite strong or quite stiff matrix, which in such a diagram shows up like these blue curves. That's also which only a mild weakening by this Berkovici-Ricard models, but if you assume these kind of geometries, you get a stronger weakening, and then we want to check how this weakening would look like if we have this kind of introduce this kind of model based on the wetness fitting data. So now here we show we are now in this fourth step. Here are the 4 steps. Model 5, a number of models, geometrical models. In some more melt is put into the tubes, and in other more into the films, but it is adjusted and fitted to the wetness data I have shown you before. So all these models, they nicely fit the wetness data. And if we plug these geometrical melt models into this effective viscosity models, we see that all show up in a bunch of curves which drop from the matrix viscosity to 0 between 20 and 30% melt fraction. And these are the bulk viscosities. Okay, but if we compare this to Hirth and Kohlstedt data, so these are lab data, they drop much faster. So we have the problem that we have nicely fitting wetness data, but not so nicely fitting rheology data. But the reason for this seems to be that these models do not account for this diffusion, this enhanced diffusion in the melt. So what we did is to, for A, which is the effective viscosity due to the strain rate energy enhancement, but if you include this effect of short circuit diffusion, enhanced diffusion to the melt, just the model by Cooper and Kolstad. So if this is the 3 grains and this is the melt in between, so along the dry grain faces, the atoms have to diffuse by solid state diffusion along the grain face, but inside the melt the diffusion is much faster. You have much higher diffusion constant, should be higher diffusion constant, or much lower viscosity by this. And as we know, for our model, as we know exactly analytically the geometry of the wetted and dry faces with this semi-analytical model, we can plug this into an enhancement factor for diffusion by accounting that these diffusive paths are shorter than they would be without melt, and this gives rise to models which, well, the previous one, if you just remember, the previous one drops from 1 to 0 this melt fraction range. So here we get a much faster drop. So we are able to produce effective viscosities which fit these rheological laboratory data as well as this wetness data, and we think that this might be quite a useful rheological model because it can be analytically described and plugged into 2 phase flow equations.
Harro, can you just say something about the form? You know, how you argued for the formula that you used. If you go back a slide. Yeah, can you say something about how you argued for this?
For this?
No. Well, for using this as the effective matrix shear viscosity.
Well, we have shorter diffusion paths,
okay,
and smaller dry faces, so the diffusion takes place only over much smaller faces, and this enhances. And I think this formula here, this formula that the viscosity, short circuit viscosity is this fraction of the viscosity of dry faces. Has been argued by Cooper and Kolstad many years ago. So this just that the dry area is much shorter, much smaller. Okay. So the problem, of course, with these now going back to the numerical implementation of these things and the 2-phase flow solutions, the problem with these viscosities is, of course, that if you get above 10 or 15% and you have these kind of curves, that you run into numerical instabilities, and this is really a problem which we haven't solved yet. So we are dealing with this kind of problems, and you will see it in the next slides that this is really a problem. Because now I want to show you some examples, ongoing research in which we use these kind of effective viscosities, although I must admit at this stage we did not include this short circuit diffusion effect yet, but this is just one next step to do, to see the effect on solitary porosity waves. So many of you may know what a melt porosity wave is, that if we have a region vertical coordinate with enhanced porosity, that you have 2-phase flow in this enhanced porosity anomaly, so the melt would move up, the red arrow. The melt fraction increases here. That means that the matrix has to decompact. The melt is leaving the lower part, so the matrix has to compact. So there will be a compaction matrix flow which goes down with respect to the reference coordinate system. And this gives rise to this porosity anomaly to move upwards like a wave. And if you choose the correct shape of this, then it moves up as a solitary wave. Here you see a solitary wave as a function of time of this porosity anomaly, how it moves up. This has been known many years ago, so these were the original papers. Using constant shear and bulk viscosity, you can get these porosity waves. Now, if you change the effective viscosity to make it depending on the melt porosity and melt geometry, what you see, the result is that with variable bulk viscosity, you get some focusing of these porosity anomalies. So porosity here, Z coordinate here. So starting with the original wave anomaly, you see that it narrows and increases in amplitude. So the effect is, and this has been shown by Richard et al., assuming porosity dependent bulk viscosity, that the shape of these porosity waves, these solitary waves, narrows and decreases. So they become more focused. So the effect of our effective rheology is to make these things smaller and with a larger amplitude. In 2D, the same effect can be shown or can be seen here. So if you start with a constant, I think this is still the constant viscosity case, a 2D porosity wave. So here the color is the melt porosity. Here the color is the segregation velocity. So if you have a circular porosity a wave, then this vertical segregation velocity is somehow elongated vertically. So that's the solution for constant viscosity matrix. So this is the vertical segregation velocity. This is horizontal segregation velocity, which is kind of going inside and then outside. If you would draw these paths, flow paths, so here you have matrix divergence, here you have matrix convergence due to the moving porosity wave.
So to me, it looks like the vertical segregation velocity that you're seeing, it seems like a dispersive behavior. What was the initial condition on this solitary wave? Was the initial condition calculated with the viscosity or with the constant viscosity?
This was the initial shape. This is with constant viscosity, this model, and the initial shape was using the constant viscosity solution by Barquillon and
So it seems to me like you're just having a dispersion.
Yes.
I mean, that's pretty well documented, right?
Yes, sure. This is old stuff. But if you and here you just the point is if you make now the step to the variable viscosity, then you have very low viscosities in the porosity wave, and you have low bulk viscosity here, and what you see is that the vertical velocity shape is not so elongated, it's more circular. Obviously the melt more effectively uses the low viscosity region, the low matrix viscosity region, and also in some cases we see that the horizontal velocities is a little bit more complicated, so the flow inside these porosity waves is more complicated, not so simple as in these classical cases. But the most important thing, if you start with a certain size of this porosity anomaly, as we have shown in this previous paper, this is just narrowing down and focusing. We get a strong melt focusing, and the melt fraction increases, and we easily come to the melt fractions where we run into numerical instabilities.
How do the numerical instabilities manifest themselves for you?
It doesn't converge anymore. We have an internal iteration between melt and melt fraction and matrix and effective viscosity, and this iteration doesn't converge anymore.
So is it like a Crank-Nicholson step and the nonlinear solve fails? Semi-implicit.
No. It's implicit.
But then when you're solving for the next time step, there's a failure to converge? Is
Yes,
that-
this iteration assumes implicit formulation, so we always take the new porosity and try to, yes, it's
Okay.
implicit. It's an implicit iterative solver. So, okay, so just starting with different initial porosities, we can make experiments, and this is just ongoing research. We can make experiments in which we use different initial viscosities, porosities, 5 to 11%, some constant background porosity, and just follow the position of this porosity wave as a function of time, and you see it slows down with time, but at the same time the porosity amplitude increases, at least for these weak viscosities, these viscosities we take out of our model, our rheology model. There we get a strong increase in amplitudes. If we take the mild viscosity law, which has been used by these Berkovici and following papers, then you get these curves which do not show a strong increase in amplitude. But the idea is to use these velocities we get here of these porosity waves and the amplitudes, and just get this dispersion in relation. So what we now plot here, so we just took this the previous experiment numerical results of the porosity of the position, calculate the velocity of this phase velocity of this wave and the amplitude, and plot the wave velocity of this 2D wave as a function of amplitude. To compare with, here is the analytical solution, the analytical solution by Simpson and Spiegelman, using this weak, mildly weakening rheology of this, which we just for abbreviation call Berkovici rheology. I think this was the analytical solution using that effective viscosity. So the dashed ones are the numerical experiments, just showing that we don't start with the correct shape of the porosity wave. So we are away from the equilibrium solitary wave shape, but the system tries to converge. So we have to work on making this thing with a better resolution. It seems to converge with time to this analytical solution. But the very the stronger matrix viscosity weakening, these are the full curves, and they start with much higher velocities, and the question is whether they approach this curve or whether they approach a different non-analytical curve with which would relate the speed, the phase velocity with the amplitude.
Two questions. One, what power did you use in your permeability?
3.
Okay. And did you include the more sophisticated shear viscosity rheology in this?
Yes.
Okay.
Sorry. Wow.
How are you choosing your initial conditions?
Here.
How do you choose what wave to start with?
We use the same Gaussian shapes. So the initial condition is no more a solitary wave, but it's just a Gaussian bell-shaped
So it's a
distribution.
solitary wave for a particular N and M choice.
Yes, but for one which assumed
Particular kind of.
particular constant viscosity. So we know we start with an anomaly which is wider than the equilibrium anomaly, and that's the reason why, as a function of time, these curves they approach these analytical solutions. But for these new viscosities, I don't think there are analytical solutions. So therefore, we have to explore this a little bit more.
That's,
And
I'll just comment. Our solution is not really analytic. By the way.
Okay, good.
It's that we got reduced it to an ODE and we computed a bunch of values.
Okay. Okay, so I should call it, how should I call it?
Sig collocation, or whatever you use.
I mean, it's analytical up to the point that you believe that we solved the ODE accurately.
Okay.
Harro, can I make one more point really quickly?
Mhm.
So, in not using the nice viscosity model that you have, one of the things that we noticed is if you go farther up, so non-dimensional porosity amplitude, that could be essentially a background peak melt fraction to background melt fraction ratio. And one of the things we noticed for the solitary waves, there are actually two branches in that space. You switch from a rising soliton to a sinking soliton, and that might be something worth exploring. What happens to that behavior when you increase the amplitude? It's a little confusing. The melt is still rising, but that doesn't mean the soliton is in sync.
That's interesting. Okay, you should show me. Unfortunately, I haven't been your talk. I bet. Okay, so this is really ongoing research, and we hope to get these curves into a better shape and to compute them until we get a more steady-state solution. I don't think we reach the steady-state solution at the end of this. So the time goes in this direction. Okay, so well, this is also shown here. More work is in progress. So this makes me coming to the last part of this presentation, in which I would like to look at the deep melting, in which the density is denser than the density of the melt is denser than the density of the solid. And this could be the case for these chromataitic melts, which have been present more in the Precambrian time, so several giga years from now, much more. Chromataitic melts have been reported, and they contain much olivine, so they they had higher temperatures at those times. So if they have been formed at higher temperatures, if we have temperature versus depth here, basaltic melts originated several tens of kilometers or 100 kilometers depth. Picrete melts originate at greater depth, but these chromataites are thought to originate at transition zone depths. And if they originate at these depths and you get partial melting in these depths, then you should look at the density, and there are recent estimates of densities of molten basaltic systems. Melt density as a function of pressure. So here you see the green one is the density from prems of the mantle, and the red ones are these new estimates of basaltic densities. And there are regions, depth ranges, where the basalts are denser than the surrounding ambient mantle. So our simple question is just what happens to the fluid dynamics, to the two-phase flow, if you have this condition of higher melt density compared to the solid melt density. So that's the reason why we just made a very simple 1D model, in which if this is temperature and this is vertical position, in which the solidus temperature is given here and the mantle temperature is given here. Here we get the onset of melting. We assume that we have a rising mantle. For example, a plume rises with a constant velocity, and you get onset of melting. You get supersolidus temperatures here, but this would be the depth range in which the melt is denser, so the melt tries to sink with respect to the rising matrix. Only above this neutral depth, the melt would rise with respect to the matrix. So here's the density of the melt higher than the density of the solid, and here the opposite. So if we take our equations in 1D, so these are the same equations as before in 1D. We non-dimensionalize these equations for time-dependent or steady-state solutions. then we get these two equations, or these three equations, and in this non-dimensionalization, so this is the relative velocity between solid and fluid, we get, in this non-dimensional equation, we get two numbers, which I called accumulation number, because we accumulate melt due to this higher density. Actually, it's the same as this, or closely related to this melt Rayleigh number. And we get, we define another non-dimensional number, which I would call compaction resistance number, which is the inverse of the well-known retention number. So these are already known numbers, but they are formulated in a slightly different way. So the idea is that this accumulation number scales with the negative melt buoyancy. So the higher this density, the negative buoyancy, the more melt accumulation you would expect in this region. And this compaction resistance number scales with the matrix viscosity. So high values mean the matrix cannot decompact or compact. So it's very stiff with respect to compaction. So let's look at some solutions. So now the vertical coordinate goes to the right. The melt porosity is shown here. And at 1 is the neutral density. So everything on the left side here, the melt is denser than the solid. Everything on the right side, the melt is less dense. So and indeed, without any relative velocity between melt and solid, you would get an increasing melt fraction, which would linearly go up. But as the melt is allowed to move with respect to the matrix, it will lag behind, and you get some increase in melt fraction in these depths where the melt is denser than the solid. So you get some melt accumulation here. So these are the regions where the melt velocity is slower compared to the matrix. And let's, but you find these kind of steady state solutions only for a certain range of these non-dimensional numbers, AC, but if you increase this non-dimensional number, you run into a time-dependent regime, and in this time-dependent regime shows you these kind of porosity waves which form as a function of time. So for a very small, for a very, very weak matrix, you get a short wavelength of these porosity waves, and for a higher, stiffer matrix, you get a longer wavelength of these porosity waves. But the thing is, the porosity waves, they are standing waves. The matrix moves through these waves, and they are standing. They are not moving. So with respect to the matrix, they go down. But as the melt accumulates, as you clearly see here or here, the width of these waves increase with time. So these waves themselves are now steady-state features. And we get time-dependent increase of the melt porosity in these waves. So you can do kind of, yes, and then you can look at the time evolution, and if you plot these results in a different way, exactly the same models or data, but now the time is plotted upwards, and the vertical coordinate is plotted to the right, and the color shows the melt fraction, porosity. If you go on such a profile at some particular time, you see the existence of these different waves, but the lowermost becomes wider and wider, broader and broader, and so it eats up all the others, and finally you get a whole area which is really has high melt fractions up to 30, 40, 50%. And depending on these different numbers, you see these different wavelengths. So this might be, this might be, we are working to fill this diagram of this, these two numbers to find the regimes in which we get standing waves which increase in width, in which accumulate melt for high accumulation numbers, or if the buoyancy is much less important, then you don't get accumulation, or if the matrix is stiffer than we are in this range, then you also do not allow this accumulation of melt fraction. So we are still working to fill this diagram. I think 45 minutes are over, and I'm coming to the end of my presentation, which had the first part in which I concentrated on shear and bulk viscosity, and I showed that we use a semi-analytical model in which the shear and bulk viscosities can finally be approximated by very simple parametric equations. We included in our model the short circuit diffusion, still have not included it into our two-phase flow models, but this is just one step, which causes problems with the stability, of course, but this has to be done. We observed strong focusing of these porosity waves if it is strongly melt porosity dependent viscosity, and we are working or see that we get new dispersion relations. And as for the higher density melts, we observed that the melt can accumulate in kind of standing porosity waves, which stand in the mantle, and the plume moves vertically through it, which may give rise to very high melt fractions, and which would be a possibility to create large reservoirs of molten material at greater depth. So this is the end of the talk, and I promised you that I should at least mention our melting benchmark, and here is the poster we present on the AGU. You don't see the contents, but if you are interested, we can talk about this benchmark initiative on mantle convection with melting and melt segregation, in which we take the original Blankenbach benchmark but switch on the effect of melting and get very interesting result, at least for the case where we have two-phase flow between melt and solid. Okay, thank you for your attention.
Question for Harro.
I had a question about the last calculation with the melting near the transition zone. It looked like the melting was sort of decompressional. That is, there was a solidus which was dropping in pressure, dropping in temperature with decreasing pressure, but that at depth the density difference was reversed. The melt was more dense than the solid.
Yes.
I mean, in a single component system, that violates the Clausius-Clapeyron equation, doesn't it? I mean, is there a problem with the thermodynamics in that?
Yes. Yes, you should, of course, make the melting relation consistent with the densities. We haven't done this in this paper. We have done this in a different paper or approach where we looked at the melting edge near the core mantle boundary, in which the densities, they were coupled to the melt law, to the solidus dependence, Clausius-Clapeyron slope, which changes with the densities. Yes, you're right. This should be included.
Other questions? So when you put in your that rheology that involved a fast path, and you said that you then had, that was where you had the numerical instability in the solitary wave experiment. So that had the ratio of the what was it, the two diameters?
Yes. Mm-hmm.
So how did you parameterize that with respect to this, the porosity parameter?
You mean the parameterization of this?
Yeah, so it was the matrix shear viscosity times the ratio.
So this is the matrix viscosity, shear viscosity?
But the one that gave you numerical difficulties.
Yes, because we use shear viscosity is equal to some parameter 1 minus a more or less constant value times the porosity. So the shear viscosity drops more or less linearly in this model. This was a preliminary model. With the Cruise's rheology, it would be slightly nonlinear. Then as the porosity comes close to zero in this iteration, it might happen that the porosity becomes negative, for example, and then you are really have a problem. So therefore you have to dampen it dramatically. So we have an internal damping parameter.
But is that an approximation for the short circuit
Yes.
model?
No, not yet. So
Oh.
this is the approximation for this mechanical weakening part.
But is that the one that gave you the numerical instability?
Yes.
Oh, okay.
Already that one. And the with the short circuit, we expect more problems.
Believe it. All right.
Did you say you expected a solution in which the melt concentration would stop increasing in the solid?
We didn't come to that.
I thought you said you sort of anticipated that. And
Yeah.
if so, if that's so, what would prevent it from growing, indefinitely to porosity of 1?
Well, because we yes, in the experiments we did so far, we did not see that the amplitude drops down. So if I go back to this dispersion curve, I think I'm going to the wrong direction. So not one back. Did I switch this off? No. Okay. So here we see that in our experiment so far, the melt, the amplitude increases. That still increases. So we don't know whether it would go up to porosity 100% or whether it would kind of even out. Well, in this last case, starting with smaller initial melt fraction, there seems to be a flattening of the amplitude. So if there is not enough, the total amount of melt in this initial anomaly probably determines whether we come to an infinitely or to a melt fraction which goes up to 100%, or whether we reach a finite equilibrium melt fraction. I think this depends on the total amount of melt we have in the anomaly. But we haven't checked this. This is just anticipated.
Margiates are denser than the mantle. How do they erupt?
The idea is that if this model is true with all the shortcomings we have, with all these, then in these are the standing waves. The lowermost wave would increase in size, and then it fills up the whole region of partially molten, of denser melt, with porosities of 40 to 60%, and then the rest of the mantle plume coming through, this produces all the melt which leaves the partially molten zone above the neutral density. So you enter new material, and it's just a reservoir which is filled from below and where the melt escapes above.
So the whole of the
And
mantle.
finally, the whole thing in 2D or in 2D models, this thing will, of course, somehow reach other regions, but this is just a simple 1D model.
So the whole of the mantle above that has to be molten, does it? Or what? I haven't understood. Because if the density, I mean, usually melts, we think of melts coming out because they're less dense than their residue. Now, if you make them more dense than their residue, how do they ever come upwards? They'll only go downwards. I don't see how you get.
Yes.
I don't see how you get the melt upwards.
It's in our simple model, we still assume a constant vertical plume velocity. We did not include the effect of the denser melt on the plume velocity. So the next step of this model would be if we increase the melt fraction here, so we have between 0 and 1, the melt is denser than solid. So all this melt sitting here would have to be introduced into the buoyancy term of the plume, which we assumed as a kinematic plume. So the plume would slow down, the plume motion would slow down, the plume would stall and somehow rearrange in a 2D or 3D way, rearrange so that this package of melt sitting there would eventually freeze and be part of a heterogeneous mantle. So this part of the melt, I don't know, that's not my computer.
It's not yours? Oh, this is theirs?
No, that's
But in the zone where the melt is buoyant, is that?
yes. The melt will move up.
Yeah, but is that come out of yet? The melt above where it's buoyant?
I mean, it requires that the upwelling of the solid material has to be faster than the percolation velocity.
Yes.
So it basically drags it along. So it's so
But
you're
these
essentially
porosities, you haven't done those.
No, wait a minute.
But such large porosities, the percolation velocity is huge. So,
Yes,
so the
and-
upwelling
but
velocity
it
would have to be,
Yes,
kilometers a year.
no, the upwelling, of course, the matrix increases. So the matrix particle comes from the left
Yeah.
with, let's say, 5 centimeters per year. I don't remember the numbers we had. Then it enters this region and then it increases by a factor 2 or 3 faster because the melt sits here and is moved through the melt like buoyant crystals.
No, I understand all that. The problem is, how does it take the melt with it? To take the melt with it, to erupt it, it's got to move upwards faster than the percolation velocity.
Well,
Probably means many kilometers a year,
no,
which is not all.
no,
I
not
haven't
many.
understood. I haven't understood how your melt ever gets to the surface.
All the melt, so we fill up this reservoir, and once it is filled up to a constant value, all the new melt coming in from below leaves it at the top. And this is just a melt reservoir in which the melt resides somehow longer. So it's just a question of melt mass conservation, because in this simple model, of course, only if we are at this kind of steady state times, we generate new melt, and at the surface of this dense melt package, there is still 0.6 melt fraction, and all the melt at that region has a positive velocity, and it crosses the neutral depth region with a positive velocity. So it's just leaking out.
Sash?
All right, just wanted to change the topic a little bit, and I was wondering if I could ask you a little bit of a technical question. So the dispersion curve that you're showing us, it's really the velocity versus amplitude. I was just wondering, when you do dispersion of the, say, frequency versus the wave number plots for this type, do you see any significant distinction between the constant viscosity case and this new viscosity model in the dispersion relation itself?
Well, we didn't look at different wavelengths and different shapes of this porosity wave, so I cannot really. These are just few models we did so far, so I'm sorry that I cannot answer on this dispersion relation.
All right, let's thank Harro again.